Welcome, everybody. It's a great pleasure to introduce Giyad Vali, today's colloquium speaker. So Giyad is a professor of physics in LMU, Ludwig Maximilian University in Munich, and he's also a director at the Max Planck Institute for Physics. He was in New York University for almost 20 years. And so over the past 2 decades, Giyad's work has been very influential in both theoretical physics and cosmology. So he's a well-known person in the field, and he has worked on very different but very interesting topics with very interesting ideas. So, and now we will give the word to him to describe his recent work, basically. Yeah.
Okay, thank you. You can hear me, right? Thank you very much. It's a great pleasure to give this colloquium. Actually, I already gave a seminar like a couple of weeks ago. It was very nice. So the subject is similar, it's the same subject, but I will discuss from a very different angle. I mean, somewhat different angle, and also will touch different topics that I didn't touch at that seminar. So it's the talk is based on a relatively recent concept, which was probably most important paper is the first one, this paper from 20, although it's based on the series of papers, but the concept was introduced there and then developed in series of papers together with different collaborators of mine. So I'm going to introduce this now. So let me start with the question: what is gravity? Okay, of course we know what is gravity. Well, first, self-contained theory starts with Newton. Okay, Galileo, Newton, and already Newton has a concept of a messenger. So Newton is telling us that if we have a source with the mass, certain mass, capital M, it produces a field, gravitational field around it, and gravitational potential, which is actually dimensionless, so it's proportional to an important quantity, which plays very important role in gravity. This is a product of Newton's constant, G Newton, and the mass or energy of the source. And okay, up to factor of 2, which is not important for this discussion. This quantity, this scale, the length scale, is called gravitational radius, or sometimes we call it Schwarzschild radius. So it's a very important characteristics of the source. So now, already in Newtonian gravity, we can view the meaning of this scale. So this tells you that if you have a source which is localized within its gravitational radius, then once you reach the gravitational radius, the Newton potential becomes order 1. In other words, gravity enters, Newtonian gravity enters in a strong regime. Okay. So now the Einstein theory of gravity, which is the current framework for at least for classical gravity, it represents a complete completion of Newton in 2 directions. First, relativity, because Einstein gravity takes into account physics of fast-moving sources, relativistic sources, and also nonlinearity. So Einstein gravity shows that gravity itself gravitates. So it's a self-interacting field. So Einstein gravity is a theory of a dynamical metric. And so usually what we do, we split the metric into a background, a vacuum, okay, and a perturbation that is produced by a particular source that we want to study. So this is delta G mu nu. So mu nu are the four vector indices, and x mu are coordinates. And so throughout this talk, the vacuum will be, whenever I discuss gravity, vacuum will be Minkowski. So asymptotic vacuum will be Minkowski with flat metric, which is Poincare, which is invariant under Poincare transformations. So vacuum is Poincare invariant. This is very useful because then we can, it gives us the power of a symmetry to understand different phenomena. Let me see. Yeah. So the connection between the metric perturbation and Newtonian gravity is well known. Essentially, the metric perturbation in non-relativistic limit is Newtonian gravity. Now, gravity is sourced by the energy momentum tensor, including the energy momentum tensor of its own. And by the way, you can reproduce Einstein gravity so consistently without simply starting with gravity and spin gravitational field and gravitational perturbation, and so consistently taking into account interactions with its own Einstein, its own energy momentum tensor. Okay. So as I said, gravity gravitates. Now, quantum theory brings some new scales in gravity. So I will keep speed of light equals 1 as long as we're in relativistic quantum field theory. And but h bar in quantum theory is non-zero, and so there's a length scale, a new length scale entering gravity, which we also call Planck length. Planck length is something of the dimensionality of length that you can construct out of h bar and g Newton, and actually is an extremely important length scale in gravity. This is 10 to minus 33 centimeters, as a matter of fact, and correspondingly, there is a mass scale that we can define, which is the inverse of that, which is a huge mass scale from the point of view of particle physics. So it's 10 to the 19 GeV, or approximately 10 to the minus 4 grams. And in units, so from now on, we can take units in which h is also 1, h bar is also 1, and so Newton's constant is Planck length square, or 1 divided by Planck square. Okay. So now in quantum theory, when we go in quantum theory, what is classically a perturbation of the metric, now in quantum theory is reinterpreted, must be reinterpreted, and it is reinterpreted as the expectation value of the graviton field. So quantum graviton field expectation value on a given state, that's a classical gravitational field. So this is the dictionary. Okay. So the canonically, so here I have normalized the field canonically. This is very important. So canonically normalized gravitational field divided by m Planck. So that's what metric perturbation is. Now, this dictionary, of course, is universal. It is not particular to gravity. So that's the way you translate quantum to classical. So the quantum field, classical fields are expectation values of quantum fields on certain states that are classical in good approximations. Usually these are states of high occupation numbers, or even beta coherent states, or condensates. So the specifics of gravity is that quantum field has spin 2 and 0 mass. Okay. Now, what are black holes in this language? Black holes are objects that are localized within their Schwarzschild gravitational radius. And now we understand in the black hole what is happening. This will be very important for my discussion. So what is happening in the black hole from the point of view of gravitational field, canonically normalized gravitational field. So in black hole background. So here's an ordinary object. So this object I'm denoting by different colors because it can have different features. And so inside there is a gravitational sphere of gravitational radius. For example, for the Earth, sphere of gravitational radius would be approximately 1 centimeter radius. Now, ordinary objects, they are way larger than their gravitational radius. And so therefore, because of this, you can see that the perturbation of the gravitational field is weak. Okay, it's always less than 1. And correspondingly, the graviton, canonically normalized graviton field, is always less than the Planck mass. So gravity is in the weak field regime. For a black hole, the story is different because black hole size, once you try to collapse a source within its own gravitational radius, it becomes a black hole, and for black hole size is the gravitational radius, and graviton, canonically normalized graviton field, becomes of order the Planck mass. And so this is the characteristic of a black hole. So the gravity is always strong near the horizon, in near horizon limit of a black hole. Okay, very good. Now there are several regimes when we discuss field theories from quantum to from classical to quantum. There are three well-defined regimes. This is again not specific to gravity. This is true for generic field theory. So the first regime is classical, when h bar is 0 simply. Then the next regime is semi-classical, where h bar is non-zero. However, we ignore back reaction from the quantum, small quantum fluctuations or quantum particles on the background. So it's like dancers. You have quantum dancers, a quantum dance on a stage, but stage is infinitely rigid. So you don't take into account back reaction from quantum on a stage. And then finally, there's a full quantum picture in which you also resolve the stage. Stage is also made out of particles, and so there's a back reaction. Okay, so these are three regimes. And now there are several features within these three regimes about gravity that are well understood, these features. So I will only discuss features that are commonly accepted. But they look contradictory, sort of. They look mysterious. Okay. So the first feature is the classical black holes. They are featureless. Basically, these are so-called no-here theorems. Several authors like Ruffini, Wittgenstein, Tedler-Boehm, others. There are a series of these. Sometimes we call them no-here theorems. Very well understood. That black hole has characteristics, only few characteristic properties. For example, it's described by the mass, if it has electric charge by the charge, and also spin. No other features, okay? Classically. Of course, per se, this is curious, but I mean, it's not a mystery. I mean, it's not a controversy or a contradiction. Okay, after all, it's okay. Because classical black hole is eternal also. Semi-classically. Now, semi-classically, we know the black holes evaporate. It's this famous Hawking result, a Hawking computation, which was done again in semi-classical limit, zero back reaction limit. So in that limit, we know that black holes evaporate thermally with temperature given by 1/r, the inverse size. Okay. Now, in full quantum theory. In full quantum theory, again, there are some well-understood features. So one is that black hole carries entropy. In other words, black hole has a huge microstate degeneracy. So what does it mean? This means that, for example, if you are an observer, so here's an observer, this Alice, and the observer is observing a black hole, a classical black hole, let's say solar mass, I don't know. And the observer thinks that this is an ordinary black hole. This is just one object, okay? But this object in quantum theory has a hidden label that classical observer cannot resolve. So in reality, it's when you are observing a black hole, this particular black hole in reality is one out of exponentially large number of possibilities of representatives. We call them black hole microstates, okay? So they have identical classical characteristics. So they are degenerate in energy or nearly degenerate. And their number is exponentially large, but they are different quantum mechanically, and this is important. Now, correspondingly, there is an entropy. Of course, once we have microstate degeneracy, you can assign entropy. Simply take a log out of number of microstates, and this entropy has a curious form. It scales like area in units of Newton's constant. There is this factor of 4. From now on, I'm going to drop it. It's not so important for this discussion, but so there is this area in units of Newton's constant. Okay, so the first mystery is considered to be this area. Why area and not something else? Okay. Now, the second thing is that, of course, since black hole has this label that comes in exponentially large number of possibilities, The entropy is very large, by the way, for a macroscopic black hole. So enormous. So this means that you can store information in this, because you and me, we can agree on dictionary, and we can say, okay, look, this label means this, and you can, for example, you can write a book in a black hole. Okay, so there is this enormous information, but now this so-called so now the mystery is that there is another sort of well-accepted statement that if I want to resolve this information that is carried by a black hole, so what can I do? So there is a black hole, and this black hole evaporates. And for example, I can just wait, an observer can wait, collect this, put a huge detector around it, and analyze these products of evaporation, and read out the information that was there in the black hole. But surprisingly, the time scale that is required, the so-called page time, actually is enormous. It's proportional to the entropy of black hole, or actually is proportional to the half-life, half decay time, not half-lifetime, half decay time. So you have to wait until black hole emits half of its mass in order to start resolving the information. Not to resolve information, of course, you cannot resolve full information because half is still there, but you can't even start before that. So what does it mean? Okay. Why this is mysterious? This is mysterious because of Taylor algorithm, right? Because you say, okay, I mean, imagine I have a book, okay? So let's say this book is like, I don't know, 1,000 pages, okay, or 100 pages. And with some periodicity, you take page after page, tear out page after page, and give it to your friend. So let's say 1 page per day or whatever. So now, normally, your friend can start reading these pages immediately. So you gave me a page from the book, sure, I can start reading it. This will not give me the entire information about the book, but I can right away start receiving some information. But on the other hand, what black hole tells you, no, you cannot, because you have to wait until the half of the pages are gone in order to start receiving information. And this is pretty mysterious. So in other words, you have an object that carries huge amount of information, releases this information, releases energy, but doesn't release any information until very, very, very late times. Now, actually, it turns out that we never asked the question, maybe this is normal. That's how it should be also for the other objects. It's not specific for a black hole. Because in that light, as I will describe, this argument looks a little bit naive, very naive. It is actually naive. It turns out that this is exactly how it should be, okay? And black holeness and gravity has nothing to do with it, okay? So the question that I wanted to ask myself was, how special are black holes, okay? Now, surprisingly, this question was not really posed. We never posed it really. I mean, now the reason was probably we thought it was obvious, okay? Because I mean, obviously, if you ask someone, okay, here I have an apple, and I have a black hole, and let's say of the same mass or same size. I mean, obviously, black hole is very different than an apple, and so what is there to ask? But this is a false statement. This is an ill-defined statement, not even false. It's just ill-defined, because we can only compare objects if we bring them into the same universality class. Otherwise, we cannot even compare. What are we comparing? What feature of an apple am I comparing to a black hole? Okay. So my idea was that there must be some universality class for objects in which they can be compared with black holes. So there must be some class that unifies black holes with other objects. And so the question, what was it? Now, so the step was like this. So we're saying the black hole entropy is mysterious. because its area, and this is the very important point, because this is the area in units of Newton's constant. But I mean, how can I even say that this is mysterious, since I don't know what other objects do? Important thing is that, of course, G Newton exists only in gravity. Okay, so this is the thing, right? So therefore, obviously, there's no G Newton in other theories. So it cannot be, the parameter cannot be G Newton as a gravitational constant. Within this entropy, when we write this entropy, if there exists an universality class, G Newton must have a different meaning. There must be a different universal object, universal quantity, that for gravity happens to be G Newton, but for other theories it has also a well-defined meaning. Okay, and so my idea was that universal phenomena that is shared by all the objects that can store information, that can, that the entropy is number Goldstone phenomena. Okay, and so let's see what we get here. So I want to interpret, therefore, first, in order to compare black holes with apples or oranges, I have to first interpret the entropy in terms of number Goldstone phenomena to bring them in the same universality class. Now, there's a Goldstone theorem, right? Well-known Goldstone theorem, which tells us that when there is spontaneous breaking of symmetry, global symmetry, there are gapless number Goldstone bosons. Now, spontaneous breaking of symmetry means that you have initial Hamiltonian or Lagrangian. Your Hamiltonian Lagrangian is invariant under some global symmetry, but a state, in particular, a state which you can approximate as a ground state, is not. Okay. For example, air in this room here, okay, breaks spontaneously Poincare symmetry, and their corresponding Goldstone bosons. These are sound waves that propagate in the air. Okay, so now black hole breaks, of course, Poincare symmetry spontaneously. And let's try to understand what's the coupling of the Goldstone boson, what's the decay constant of the Goldstone boson. Now, the Goldstone boson is always characterized by the scale of symmetry breaking, and that is also a coupling of a corresponding Goldstone boson. In other words, that's the price you have to pay in order to excite a corresponding gapless mode. Okay. Now, the black hole breaks Poincare symmetry spontaneously. And the order parameter is the graviton field, canonical normalized graviton field. The graviton field reaches M Planck, that's at its maximum, okay? And that's the scale of the Goldstone for Poincare of spontaneous breaking of Poincare symmetry by a black hole. Now we understand what's the meaning of Newton's constant. Actually, Newton's constant, of course, is constant of gravity, obviously, but it's also, for a black hole, it represents the coupling of the Goldstone boson, a broken Poincare invariance. So therefore, black hole entropy I can equally write as area in units of Goldstone coupling. Why is this form very important? Because now I can compare with other objects. Now I don't need gravity. Now I can go in arbitrary theory and see what happens to other objects, because the Goldstone phenomenon is universal. Now, so I formulated the bound, and then I gave arguments. I think I've proven it, more or less, okay? So that this is actually the maximal entropy that, regardless, any object can have in any theory, regardless of gravity. So in other words, if you have an object, the maximal entropy is given by the area divided by the Goldstone, by the coupling of a Goldstone. Now, by the coupling of all Goldstones, so if you have many Goldstones, you can write for all of them these bounds, and the one that is the weakest will be the bound. But universally, there is Poincare Goldstone, so it's always well defined. And so the objects which have maximal entropy of this type, I call them saturons. And so, yeah, their entropy is area in units of Goldstone boson, Goldstone coupling. This is the number of space-time dimensions. Again, here, just to, sometimes you can use different notations if you like. For example, okay, area always scales like the radius in power d-2. G is Goldstone coupling. However, sometimes you can trade Goldstone coupling, as you know very well, for example, for pions or other Goldstones, with the scale of Goldstone. So the universal relation is that Goldstone coupling is 1 divided by the scale square of the Goldstone. And the scale we call Goldstone decay constant, just a common usual name, just to fix terminology. Now, as I said, any self-sustained object breaks Poincare invariance, Poincare symmetry spontaneously. And therefore, this is nice because Poincare Goldstone is unambiguously defined. Okay, so it's always defined. For example, for instance, if you have a system with n quanta, for instance, a bound state of n weakly interacting quanta, you can figure it out. It's straightforward that the Goldstone coupling of Poincare Goldstone would be 1 over n times the area. Okay, so now so it turns I've studied my collaborators and I in different combinations. We studied many examples of saturons in many different theories. So the role of saturons could be played by solitons or instanton-like objects or other bound states, and without any exception, they always have the same key properties as black hole has. They have information horizon. Information is carried by the Goldstone modes, very similar to a black hole. They evaporate thermally in semi-classical approximation. Their entropy, of course, is area. This is obvious, and by default. And information retrieval time is also Page's time. Many other things. So virtually, I mean, I'm not aware of any property, any key property of a black hole that are not realized by all the other saturons. So it looks like that black hole properties have nothing to do with gravity per se. Okay. I mean, I'm talking about key mysterious properties. Of course, gravity is gravity. I'm not saying that. I mean, that's obvious. But these key properties, they are not originating from gravity. So what we are discovering is that they are originating from this phenomenon of saturation. Okay, so whenever state saturates this maximal entropy given by this expression, area in units of Goldstone decay constant. Now, so what happens is that it's very interesting if you watch theory by theory in different theories. It's very interesting how theory maintains this bound. Okay. Now, this story with saturations, therefore, is not only interesting for gravity. Of course, it's interesting to understand gravity in terms of saturation and black holes. But in certain sense, it's even more interesting for other theories, because now we understand certain phenomena in other theories, and I'll give you one example, in terms of precisely the saturation. So in other words, you see what is happening always. So when you have a theory, right, it doesn't matter which theory, it could be relativistic quantum field theory, could be many body physics, non-relativistic quantum field theory. I mean, I'll give you examples later. So you can have this type of saturated states. This is also very nice because we can study them in laboratory, okay? In tabletop, I mean, in not necessarily in accelerator. We don't need accelerators for them necessarily. Although also in accelerators, we can study them. And so what happens is this, right? So whenever we have a given system, we describe the system in terms of degrees of freedom, right? So we always have some degrees of freedom, which are good degrees of freedom. Good degrees of freedom usually are weakly interacting degrees of freedom. And so when we, for example, we compute loop expansion is good, perturbation theory is good, etc., etc. Now, in terms of these degrees of freedom, you form a state, for example, a soliton, and naively it looks like that there's no problem. You can go over this bound. I'll give you an example. So you go over that bound. But what happens simultaneously if you try to go over that bound? Theory will change the regime. So those degrees of freedom that you had will no longer be good degrees of freedom if you try to push the theory beyond, but the bound is never violated. So the entropy at its maximum is this. Okay. The theory will change the regime. And so there's one very intriguing example of that, okay, which I will discuss now. This is a connection between this phenomenon of saturation and confinement in QCD. Now, in QCD, QCD is probably the best understood theory that we have of one of best understood theories, certainly, that we have, which works and is calculable in proper limits. So it's a theory of strong interactions, okay? And so the messenger is a color. So there's a new quantum number color, and particles are exchanging this the gauge bosons that mediate color, okay? Now, so and in QCD there is a well-known phenomenon of change of regime, a beautiful phenomena which we call confinement and generation of the mass gap. Now, what happens? QCD has a scale which we call lambda QCD, LQCD, the length scale. Okay, it's approximately in real QCD, it's approximately 10 to the 14 centimeters. But this is a property of huge class of gauge theories. Now, at short distances, you have theory of gluons and quarks, and those are good degrees of freedom. For example, if you are a short distance observer, there's a whole universe inside this QCD scale. For example, if you imagine some color sources, they produce a classical color field, good approximation classical color field, and so on. But if you try to, let's say, make the observations, your observation at larger distances, the states become colorless and the mass gap is generated, okay? So the theory locks up the color in non-perturbative, in states which from the point of view gluons and quarks are non-perturbative. What happens is that they exchange places. Now, good degrees of freedom are composite objects, such as mesons, baryons, glue balls, and so on, okay? So sometimes pictorially, we like to illustrate this as a sort of a stretching of the QCD flux tube, color flux tube between the sources. Okay, so I will discuss. So in order to understand connection between saturation and confinement, okay, instead I've considered a cousin of ordinary QCD, which is we do it very often. This was pioneered by Toft, this framework. So this is a generalization of ordinary QCD for a large number of colors. Okay, so instead of 3 colors in ordinary QCD, we have 3 colors. I don't know, red, blue, green, whatever. But now we can have n colors. And actually, for large n, it turns out the story becomes simpler in certain sense and also very transparent in certain sense. Okay. Now, so here is the illustration of this point. It's very easy to understand. So gluons, they carry color, anti-color. Okay, so for example, if I have a gluon, I can always label this gluon by a pair of colors. For instance, red, blue, for instance, red, anti-blue. So the arrows indicate color, anti-color. So this is an interaction between gluons. For example, if 2 gluons, let's say green, let's say red, blue, a red-blue gluon can scatter off a green-red gluon, green anti-red, and produce two other gluons. Now, at large n, what happens is that some of the colors are fixed of the other gluons, okay? Because the color flux is conserved, and that's a beautiful picture. So it's as if when you have a gluon, as if there is a tube in which 2 colors flow, okay? And so the 2 colors, let's say green, let's say blue and green, they are fixed. But now it's produced a new color, and this new color can take any color, any value. So therefore, there are 2 types of couplings immediately that you can define. Okay, there is a 2 gluon into 2 particular gluon strength, and that is measured what we call alpha QCD. Okay, so for example, if I fix a particular color here, whatever color you want, then there will be coupling strength. The amplitude of this process or interaction strength will be given by alpha what we call alpha QCD. However, because this color is free, there are all possibilities to be produced, okay? And so there is a summation over n, and this gives you what is called sometimes a Toft coupling or collective coupling. And this is very nice. So you see what happens is that a fundamental coupling, alpha, can be arbitrarily weak, but theory is non-trivial nevertheless, because if colors are large, okay? So there is a very nice limit in which everything reduces to, the whole dynamics is reduces to dynamics of the collective coupling, of the Toft coupling. So formally, you can take limit when alpha goes to 0 and goes to infinity, and lambda is fixed. And this coupling runs, okay? It's a running coupling. Runs means, what does it mean, runs? It means that effectively the strength of this collective coupling depends on the momentum transfer or the scale at which you are doing measurement, which is the same thing, okay? Let me see. Yeah. Okay, so now, so this theory, again, there are certain features of this theory that are commonly accepted and relatively well understood. And so we know that this theory confines, just like ordinary QCD. I mean, that's why this theory is also interesting, because it's like a laboratory for ordinary QCD. Confines at the scale where lambda collective coupling becomes order 1. So you see, collective coupling sort of is a measure of the regime. So once collective coupling becomes certain critical value, order 1, the theory confines. Okay, so this is what these are the sort of things that are pretty well accepted. But now there is an interpretation. The new thing is an interpretation of this in terms of saturation, okay, of saturation of the entropy, okay, because sometimes people use in QCD the term saturation in terms of occupation number. I'll get there. This is not the same thing, of course. Here is the saturation of this particular entropy bound that I'm talking about. So it turns out that there is a correlation. So there is a high occupation number, a certain gluon state, and this gluon state, naively you can think that you can increase the entropy of this gluon state at degeneracy arbitrarily, but no, precisely when this degeneracy hits this bound that I gave you, the Goldstone bound, exactly the same bound as black holes saturate, theory becomes confining, okay, and it's very nice. So here's more to make it more precise. So actually, here's the point. If I count entropy of a gluon state, the gluon state has large entropy. Why? Because gluon state breaks Poincare invariance, of course, spontaneously, but it also breaks global color symmetry spontaneously, because they are Goldstones. Why? Because these Goldstones come from the fact that the gluon state, you can rotate it in color space, and there is a huge degeneracy because of that, exponentially larger degeneracy, similar to a black hole, okay? And what is happening is that and that depends on collective coupling, okay? Of course, I'm skipping technical details. There is a beautiful expression, and the expression is this: if I try to push collective coupling to be large, meaning that, okay, lambda, the Toft coupling large, the entropy of this gluon state goes as like a black hole area divided by G Goldstone of Poincare, or other Goldstones, which in this case they are the same, and then there is a logarithmic growth with lambda. But naively, if you don't know anything about confinement, you would say, okay, look, in this theory, I can have an arbitrarily large entropy for gluon states, because I can take lambda arbitrarily large because I simply can increase number of colors. But that cannot happen, because as we know, when lambda hits the critical point, the theory becomes confining, and the further growth of degeneracy of the color degeneracy is shut off. So this is the regime change. This is a beautiful example of how a saturated state is correlated with a very interesting phenomenon, very important phenomena of the regime change. So in other words, confinement. So again, in this picture, I want to reiterate, because this is very important. So again, these are the scales So this is lambda QCD. So imagine that we are some microscopic observers much smaller than QCD length. Okay, QCD length could be whatever. It could be galactic size in a theory, whatever. And now imagine you are in theory in which in which you have a small observer, tiny observer, so that the ratio is like galactic scale to human size. And so these humans are doing experiments with gluons. They see that they can put together many gluons and create a state with high entropy. But they will never be able to violate this bound, because as soon as entropy of this state reaches this bound, a theory enters in the confining region. Okay, and confines and becomes colorless, and you have change of degrees of freedom. So now now you see how beautifully this saturation works in two seemingly very different theories, gravity and large QCD. So in gravity, what happens? In gravity, if you have an object and you try to give it a maximal entropy, so you keep increasing the mass of this object, let's say you put more and more stuff in it, more and more degeneracy, at some point it will collapse into a black hole. Precisely when you saturate the bound, this will become a black hole. Then if you will try to increase the entropy of a black hole by putting more stuff, black hole will grow. Okay. In QCD, there is a similar self-defense mechanism. So instead of forming a black hole, theory confines and forms glue balls and mesons and other objects. Now, of course, there's the natural question. I mean, is something like this, are there such states, saturated states in ordinary QCD? Actually, the answer is, there's a huge evidence that indicates yes. The answer is yes. Raju Venugopalan and I, who wrote a paper recently, arguing and showing that so-called color glass condensate state in ordinary QCD actually is a good candidate for that. Okay, for being a saturated in this sense, in the sense of this goldstone entropy. Okay, because as I said, people were using term saturated, or saturated could be applied to arbitrary thing, in particular to occupation number. That's a different saturation. So this color glass condensate was already called a saturated state with saturated occupation number, but it's not. It was never called state with saturated entropy, because there was no bound formulated in this language. And so our point is that we came to this from slightly different perspective, like trying to make direct analogy between composite picture of a black hole okay, we had previous originally a long time ago with collaborator of mine, Cesar Gomez, but and from there, but okay, at the end of the day, the whole picture matches very nicely. Okay. Now let me, before I finish, I think I'm doing fine in time, right? Okay.
Yes, right now, yeah. I think you can go on up to around, say, 10 more minutes or so if
it's plenty.
you want.
That's plenty.
Yes.
Yeah. No. So that's so okay. So now there are some interpretations, of course, of this. Again, as I said, there are other interesting effects. Of course, unfortunately, obviously, we cannot discuss everything in details. But for example, one question is, what can we learn about black holes beyond this very interesting universality? One important message that I take from here for black holes is the following: that okay, so what do we know is there's a fact that black hole enters in the same universality class as the saturons. That's a fact. Now this fact requires some interpretation. Okay. Now, because then we can learn something about black holes, which we didn't know before about black holes. Now, one generic feature of the saturated states is that they represent states of high occupation number of soft quanta. Soft, what does it mean? It means that of the same softness as the size of the object. In other words, these are composite objects with the typical wavelength of constituent quanta, which is given by the size of the object. And so therefore, it's natural that now black holes should be interpreted as in a similar way. Black holes should be interpreted as composites from this analogy, okay, as composites of high occupation number states of gravitons. Now, actually, this idea about black holes being high occupation states of soft gravitons was suggested completely independently from this saturation discussion. Before, in 2011, I collaborated, Cesar Gomez and I, we suggested this picture from a completely different perspective. And by now, there is a significant evidence that this is a correct picture of, okay, correct, what does it mean correct? Correct means when I have phenomena of nature, it has certain aspects. And so the bulk of the phenomena, if theory describes bulk of the phenomena, this means that this is a good description of that object. Okay, so on the scales of a black hole, this picture of composite picture is it essentially explains everything we know about black holes and also predicts some new features of this. So there's one message I take, that saturation now gives a completely independent supporting point to this idea. But again, I mean, there may be other ideas. And finally, okay, let me just give you a picture and I'll finish with this. And so, for example, these are, I mentioned about laboratory studies of saturated states in non-relativistic systems. And we identified several examples of this, that even simplest bosonic systems with certain properties they can be used for creating saturated states in laboratory. For example, here I'm showing you a simplest system you can imagine. These are bosons with delta function type attractive interaction in the box. Okay, and this system has states that are critical states, because saturation requires combination of two aspects. One is necessarily you need some Goldstone-like gapless excitations, and the second thing is that the diversity of those excitations should be sufficiently large in order for entropy to saturate the bound. And so the first necessary ingredient is to have these gapless excitations, and you see very clearly. So this is a critical state around which this gapless excitation emerges, already for sufficiently small number of constituents. It's pretty impressive. Okay, so you see that once you are away from this criticality point, there's no gapless excitation. The oscillation frequencies are high, and yeah, beyond they are also high. But near criticality, there is a frequency that enters, a very low frequency, which this frequency becomes gapless in large n limit. Okay, so therefore, yeah, and then you can also construct the wave function of this state. This is a rainbow of these microstates of this state of this saturated, a candidate for the gapless for the critical saturated state. Okay.
So sorry, okay. In the previous transparency, can you explain the axis, like the one before this here?
Yeah. So
what is being measured basically?
Collective coupling, lambda. That in QCD would be collective coupling. Remember, I introduced collective coupling,
yes,
which is fundamental coupling times the occupation number. For this system, is fundamental coupling times the occupation number. So the critical coupling. So it's very similar to confinement, but realized of course, in a different language and in different terms. So in other words, what happens is that collective coupling, when it reaches certain critical value, which is usually order 1, up to some factors of 2 and pi's, gapless modes emerge in the system. Okay. Now for gravity, that critical coupling, the collective coupling being critical, is precisely point of black hole formation. For QCD, that's the point of confinement at large M QCD. Okay, or in the ordinary QCD, we think that that's the point of color glass condensate formation, where color glass condensate forms. And here it's the simplest system with cold bosons, just simply bosons, non-relativistic, interacting with attractive delta function potential. So here, yes, again, for the critical coupling, there's a critical point where the gapless mode emerges. Okay.
And this N2 is what?
Sorry?
The N2, the vertical axis?
No, these are because the system has certain because the system is a system of bosons, right? And these bosons have different momenta, obviously, right? So the state is reached for certain occupation numbers of different momenta because there is a distribution. Okay, so there is so this particular state is characterized by occupation number, which is given by certain by frequency of the certain momentum modes, which is the lowest one. Because what happens is that since the system breaks, because you have occupation number of modes, the system breaks, obviously, translation and time translation invariant, also space translation invariance. So correspondingly, the gapless mode can be the modes that normally in the vacuum would have a high gap now can become gapless. So it's that's why it's also beautiful. The critical point is reached. Normally, you would need a lot of energy to store information in this state, but now because the same excitation is gapless, now it's very cheap to store information in the same state. Okay, yeah, thanks for the question. Okay, yeah, I'm concluding. Yeah, so if there will be questions about okay, so, of course, the bound and the proof of the bound, it requires certain things. I'll be happy to answer if there are certain questions. Thank you very much. Okay.
Thanks a lot, yeah. So, okay, so if there are questions, please.
Yeah, I see one question.
Okay,
Matti?
Go ahead. Matti?
Yes, you said that the corresponding other what was it called? Something, sorry. Anyway, you said that they radiate out energy as well. Yeah, so does that mean that the proton would evaporate and would have a certain temperature?
Exactly. For example, even actually beautifully that you can even see in the in this model. So beautifully, this system, once you bring the system to this critical state, it starts to evaporate, deplete. So what it does, it starts to create quanta above the ground state, and it's very similar to Hawking evaporation, actually, beautifully. So what is incredible for me is that already such simple systems that it's very hard to imagine anything simpler than 1+1 dimensional box with bosons. The same is true in relativistic 1+1 dimensional theory. My collaborator Otto Sakhalashvili and I, we wrote a paper about Gross-Nivier model. So Gross-Nivier model is a well-known model for people that like Lagrangian physics. It's a theory in 1+1 dimensions, asymptotically free and calculable. So in that theory, essentially everything we need is known. And in that theory, you can see beautifully that all the features of black holes are given by this 1+1 dimensional bound states of Gross-Nivier. So here it's even simpler because Gross-Nivier is a relativistic theory. This is a non-relativistic 1+1 dimensional system. And yeah, it's indeed incredible how powerful this saturation phenomena is. Yeah.
I was asking specifically about protons.
Proton?
Yes.
No, proton,
said
proton
that,
doesn't evaporate. No, proton doesn't evaporate, no.
But it sounded like, okay, did I misunderstand you that the colorless state that comes from QCD had the same properties? I thought that
no,
would
I didn't
imply.
say that. No, thank you for asking. No, I didn't say that. That would be no. So so what I said was there are two different things. Okay, so what I said is the following. So even if you are in theory of pure glue, by the way, to have proton you need quarks. So here I was already discussing theory of pure glue, right? Because you have confinement already in if you have a theory without any light quarks or without any quarks whatsoever. You do have confinement in QCD, right? So here I was ignoring quarks. I assume that there are no quarks, let's say. This is large MQCD, only purely gluon states. So there, I just established a correlation between the saturation of the entropy bound, of the color entropy bound, and confinement. So ordinarily at large distances, we are observing colorless states, and those states, because they are colorless, there you don't see this color entropy. That's precisely the point. So that's precisely how theory defends itself from violating the entropy bound by creating a mass gap and the colorless state. So to really count entropy of a gluon state, you have to go at very short distances. So you have to be an observer for which gluons are good degrees of freedom. So once you are in the shoes of that observer can create a gluon state. Of course, that gluon state will have a wavelength much shorter than the QCD length, obviously. This is, for example, what happens in color glass condensate in ordinary QCD. The color glass condensate in ordinary QCD forms for the saturation momentum, which is higher than the QCD scale. So therefore, this all is for an internal observer that can distinguish colors. So that's the connection. Now, colorless states, if you introduce quarks, I unfortunately in this talk I didn't have time to discuss that, but there is a beautiful thing about the entropy of the colorless states, but for that you need quarks, for example, to have proton. Now in large MQCD, we can have baryons, right? So for example, proton is a baryon. So for instance, if I take large MQCD and I add quarks, then theory gives me colorless states, but they have flavor quantum numbers. So what happens now is that the entropy of a baryon is because of flavor quantum numbers. And the same holds there. You can see that exactly the same thing is. If you try to make baryon to violate the entropy bound, so in other words, if you try the flavor quantum numbers of baryons to be too high, theory will respond by becoming asymptotically non-free. And in that theory, you will not have baryons. That's another beautiful way how theory tells you that you cannot have too high entropy in baryons. But for that, in order to have entropy for baryons, you need flavor quantum numbers. Now, in ordinary QCD, what happens is, as you know, quarks are massive. And because of this, baryons are not strictly degenerate. Therefore, for example, if I give you a baryon decuplet, yes, baryon decuplet, you can think of it as a microstates of one baryon, except these microstates are split because quarks are massive. So therefore, real QCD in baryon sector, unfortunately, is not a good example for saturation. But it makes up for it by going into color glass condensate of gluons at short distances, because there it provides example of saturation. Okay.
Okay.
Ariel?
Thank you.
Thank you for a very nice talk. Yeah, so you ended up with a cliffhanger saying that there could be implications for both cosmology and collider physics. Could you give us a flavor for what we should be looking for?
That's right. That's correct. So, so for example, there are very nice discussions about saturation in cosmology, because, for instance, it turns out that the states like the Sitter state, if I think of the Sitter state as in terms of quantum theory, and obviously we have to think in terms of quantum theory, the Sitter state has this Gibbons-Hawking entropy. And actually, the Gibbons-Hawking entropy again saturates the same Goldstone bound on entropy as a black hole. So from that point of view, the Sitter state is also a saturated state. And actually, then this allows to understand a lot of properties of the Sitter. For example, particle creation, Gibbons-Hawking particle creation, etc. Again, to understand in terms of this universal property of saturation. And also, one very important piece of information that saturation gives about the Sitter state is that the Sitter state cannot be eternal. So in this matches very nicely the other argument that I had about from S matrix, because another argument comes from S matrix that the Sitter state cannot be eternal. This S matrix is completely independent argument, has nothing to do with saturation. That also indicates that the de Sitter state cannot be realized in quantum gravity, because quantum gravity is defined in terms of S matrix. And very nicely, the saturation essentially matches that argument. So saturation also, in other words, the message is very simple. So the saturated states, unless they are critical, for example, extremal black holes or solitons, which have some topological quantum numbers, then they cannot be eternal. They always evaporate. Okay, so de Sitter therefore cannot be eternal. So that's another interesting piece of information. Mm-hmm.
Thanks.
Boo?
Yeah, you emphasize the role of Goldstone modes. So I'm wondering if you can say anything about other aspects, properties of a theory that is needed to get these saturated objects. It's not enough with having Goldstone modes, I suppose, or is it what you need more?
Yeah, so in all the examples I gave, so in other words, as I said, why it's useful to formulate the bound in terms of Goldstone, because Poincare Goldstone is universal. So there is no device, a self-sustained object or a device that is not breaking Poincare symmetry spontaneously. So that's a universal characteristic of any object, regardless gravity or other theory, etc. So that's why it's universally very nicely expressed. The bound is very nicely expressed in terms of Poincare Goldstone. Now, your question is whether, so however, the existence of Poincare Goldstone is not telling you, it's a measure for the entropy, because of very good reasons. I didn't have time to discuss it because it's related with the unitarity of the scattering amplitudes, etc., etc. It's a very good measure for the entropy, but it's not the only source that contributes into the degeneracy. So therefore, the picture is like this. Poincare Goldstone universally present in every theory. So it's a very nice measure of maximal entropy. However, depending on a particular theory, the degeneracy may come from Poincare entirely, like that happens for a black hole, or in black hole, it comes entirely from breaking space-time symmetry, or it can come from other Goldstone modes. Okay, so for example, like in color glass condensate, or in flavor, in case of flavor of baryons and so on, or then this is probably what answers your question. It may come from the modes that become gapless only exceptionally at a very special point, at a critical point, and beyond the critical point, they don't have interpretation in terms of Goldstone modes. Okay, so that can also happen. So, for example, this is a very nice example of that. So for example, if I have a theory of cold bosons, in this theory of cold bosons, there is a mode that appears at the critical point, which has interpretation in terms of Goldstone only at that critical point. Okay, so it doesn't have interpretation in this regime if I'm away, or in this regime. So that's different from QCD, because in QCD you always have Goldstone interpretation. Doesn't matter whether your bound state saturates the bound or not. Even if you are away from the bound state, or away from saturating the bound, you still have Goldstone bosons. So for example, you have because there is a glue embedding of glue ball of gluon condensate in the color space, you always have this moduli space. You always have Goldstone bosons. But universally, what happens is that once you are at the saturation point, the Goldstones emerge even if they are not away from the saturation point, because modes have to become gapless. Okay, I don't know if this answers your question, but yeah.
Fine, thanks.
So I mean, that's in certain sense that's a good example, because I am not aware of any model. I studied many examples in the papers, also I'm not aware of any model which has saturation but doesn't allow Goldstone interpretation of these gapless modes. I've not seen anything like that, but I don't have a theory. So maybe there is a model in which gapless modes emerge, but they they don't really allow nice goldstone interpretation. There could be, but.
And what about the other direction? If you have goldstones, what more is required to form saturated objects?
Yeah, so so the saturation is an interplay between number of goldstones and the strength of the coupling of the theory. Okay, so and it's very nicely expressed in terms of this collective coupling. So usually you can form a combination, number of goldstones, which usually is related with QCD is related with number of colors. So number of goldstones times the coupling, and that collective coupling is usually the good measure for saturation. Okay, so there's always some collective coupling that measures the saturation. When it becomes critical, that's when you get saturation. Yeah.
Okay, thanks.
Thank you.
Nirmal?
Yeah, thanks for the nice talk.
Thank you.
I had one question. Did I understand right that the entropy is maximal at the basically at the critical condition, and like if you're at scales lower than the critical condition, then the entropy drops? And if that is true, then time can be interpreted as the gradient, or the arrow of time is basically given along the gradient of entropy. So does that mean that time flips, or the direction of, or the arrow of time flips within and outside the critical point?
Well, thank you very much for this question, because actually this allows me to clarify again. So in other words, what I'm saying is this. So let's think in terms of this, right? Let's imagine that this is a system where we have here there's a saturation point, and the wave system is not saturated. Now, what I'm saying is the following thing, that it's not that absolute measure of entropy is important. For example, when black hole decays, of course, entropy increases. Entropy always increases statistically. What is important is comparison of entropy with the bound. But bound depends on the size of your system, right? So because it depends on the area and depends on the goldstone coupling. So I'm not saying that entropy cannot increase. Obviously, if I have a saturated system when it evaporates, for example, if I start with this point and I let the system to deplete, obviously entropy will increase, but it will become much less than the corresponding bound for that new state. So this is very important to understand, okay? So it no longer be a saturated state. And that's why, so therefore, there is nothing particular about arrow of time or anything like that. Arrow of time, maybe it could be interesting to see in particular system. For example, if you have a system which somehow moves towards saturation and then decays and stuff, you can, there you can study how in connection with the arrow of time the system will be. But again, what is very important, I'm saying that at the saturation point, the entropy is maximal for given parameters, for given decay constant of goldstone, for given coupling of goldstone, and for given area of the system. I don't know, maybe I didn't have time to show this picture, but usually one correlation, very nice correlation, of why the entropy bound is saturated is in the scattering amplitudes. So what happens is that if you create a state which saturates this entropy bound, then there is in one-to-one correspondence, there is a scattering amplitude of usually 2 to n, where the final state can be interpreted as production of that maximal entropy state, and that scattering amplitude saturates unitarity, okay? So the entire cross-section is dominated by that particular channel. This is what happens, okay? So in other words, typically, the scattering amplitude cross-section at large n, the scales like this, and you can also, where alpha is the dimensionless coupling constant of goldstone, actually. It's literally this maximal entropy that I gave, just written in units of dimensionless coupling. And you can also see why bound is pretty robust from this argument, because otherwise the system would violate unitarity. Of course, system cannot violate unitarity, and therefore the entropy is maximal at that scale. Yeah. Okay.
Okay, thank you. I understand that the maximal entropy value itself keeps changing depending on the evolution.
Exactly.
Of the
Depends
system.
on the size of the system and depends on the goldstone decay constant. Goldstone coupling.
Yeah, thank you.
That's right. Mm-hmm.
Yeah, sorry. Yeah, I have a question. In fact, I have many questions, but I can maybe ask one question.
Sure.
Oh,
Yeah.
sorry. Let me. Okay. Dongwon Kim, you have a question. Please
Yes.
go ahead.
Yeah. Thank you so much for the nice talk. I
Thank
just
you.
have I guess some kind of a similar question from earlier. I think you mentioned about the statistics and cosmology as an example for the saturation. But what about if we talk about this in context of LHC physics? This was also listed
Yes.
as like implication.
Yeah, indeed. So there's one implication. So in beyond the standard model physics, we can have examples of saturated states which are relevant for LHC energies. And but by the way, this cross section also tells you why they can be very interesting, because saturated states are the ones for which the suppression is fully compensated by the entropy. So they have so high entropy that even though state looks like classical state, it can be produced in the collision of even two particles because of maximal entropy that it has. And so from that point of view, yes, it's very interesting from the point of view of LHC. Now, within the standard model, as I said, the only candidate I know is color glass condensate. Now, color glass condensate actually has been experimentally, there are indications that it does exist for DAISY results. So that happens at energies lower than LHC, because that's where the saturated scale is for ordinary QCD. So in ordinary standard model, I'm not aware of any strictly saturated state. Okay, so that's why this requires going in physics beyond the standard model. I'm talking about LHC energies. So there is no obvious candidate in the standard model for a saturated state around LHC energies. But in theories beyond the standard model, absolutely, there are candidates, and that's why it's very interesting to look for the signatures of those. I gave some of the signatures in the paper because they are very sharp resonances and so on. It's very interesting the way they are produced. It's very interesting the dependence of the cross section on the center of mass energy. They are very sharp, extremely sharp resonances. These saturated states. Okay, and for example, things like that. Yeah.
So, thank you very much. Yeah.
Thank you.
So what about black hole production in LHC then?
Yeah, black hole. I mean, that has been, of course, that. I mean, the black hole production we predicted in our large extra-dimensional paper. Actually, already in the second paper we mentioned with Ignatios Antoniadis and Savas and Dimopoulos and Nimar Kani-Hamed. We have a paper in which actually we even said in the abstract that obviously, of course, if we lower the Planck scale, then black hole production can take place around LHC energies. Yeah, that goes in the standard category. So black holes are saturons, so correspondingly, the new angle that saturation brings to this is that saturation allows us to understand why black hole production is indeed happening because of precisely this saturation nature. Actually, I can mention that we have computed the 2-to-n scattering process of which describes black hole formation in two versions we computed it in quantum gravity and we computed it in string theory, and the results up to 1/n are the same. And so indeed you can see that the cross section behaves like precisely like cross section of that you would think in terms of saturation and in terms of black hole production. So this computation has been done by at least by two groups, and yeah, so it looks like 2-to-n process indeed describes black hole formation correctly. Yeah, so that's additional support for saturation to the fact that black holes are saturated states. Yeah.
So then, like for realistic GR, what is the threshold? So the threshold is like you will get the standard threshold basically.
Yeah, in realistic GR, if it's pure gravity, then the threshold for seeing something non-perturbative, of course, is very high. It's around Planck scale. So it's, of course, for collider physics is hopeless. I mean, cosmologically, it may be still interesting, obviously, because in cosmology you can have center of mass energies which are very high, even in high energy cosmic rays, maybe. Unfortunately, statistics is not so good in very high energy cosmic rays. The problem is that not because there are no very high energy cosmic rays, but because when they enter atmosphere, they have many soft interactions. So you don't have interactions with really high momentum. The interactions with high momentum transfer are very rare, and so on. So therefore, yeah. So yeah, in pure gravity, black hole production, yeah, below Planck scale is if we don't have any other modification, no, yeah, it's very hard to see. Yeah.
Okay, so then maybe I ask one last question if there are no other questions. I think, yeah, you essentially clarified this partly in connection with Booth's question. So what I had in mind was that in string theory, there are these black hole models, basically, where you have these brain collections and all that, that look like a black hole, but then you can also do a microstate counting.
Yeah.
And the microstates in general, at least the cases I'm familiar with, they do appear like Goldstone modes, but not of the 4-dimensional Poincare group.
Yeah. So indeed. So in the case of in the string theory, we have examples when we can explicitly count number of microstates. Of course, there are still some assumptions go there. Yeah. This is important. Now, unfortunately, this has been done only for extremal cases. Okay. Now, extremal. Basically, the way it works is like that. In string theory, we have these D brains, very nice objects, which have this feature that they are like Dirichlet boundary conditions for open strings. And so what happens is that if you put, which are essentially they are solitons, okay? It's okay to think about them as solitons. And so the way it works is like this. If you put stack of D branes on top of each other, because they are very special supersymmetric BPS objects, BPS means Bogomolny Prasad Sommerfeld bound, which was invented for monopoles and etc. So what happens is this, that interaction in exact supersymmetric limit, interaction between two D branes is exactly compensated. The gravitational attraction is exactly compensated by the exchange of a form. Usually they exchange some sort of like a gauge field, a form. And so there is no force. So therefore it's like they're completely neutral. So now if I have several D branes, I can do the following trick. I can put them on top of each other, but then I can slightly displace them, right? And now if I have n D branes on top of each other, they are n square moduli that count their displacement. And these moduli are like Goldstone, these are like Goldstone modes of the internal symmetry. And so those are the ones that contribute. Now, the point there actually confirms this point in a sense. Now, unfortunately, going beyond criticality, going beyond the, big extremality, I mean, is not possible. Nobody has computed anything there because corrections are not controllable. But if we take this extremality, what happens is this, that the gravitational part of the entropy would be fully accounted by the Poincare part. But what happens is that the number of zero modes that Poincare Goldstone gives is exactly matched by the number of these internal Goldstones. This is because of too high supersymmetry. Because of n equals 4 supersymmetry, this is what happens. So the Poincare Goldstones, the Goldstones created by Poincare, they sit in the same multiplet as the internal Goldstones. So therefore, it fully matches this argument that Poincare Goldstone accounts for the zero modes coming from the Poincare accounts for the entropy. Actually, that's one very nice proof of this in the extremal case, right? Yeah. Okay. I mean, usually it's not interpreted in that language. I mean, I am interpreting in terms of Poincare, but it goes through precisely. Yes.
Yeah. So I think I find your picture very interesting, essentially from this perspective also, that during like for 20 years or so, people have looked at string theory black holes, where you look at special cases and you can get the right entropy, but one doesn't know why one is getting all of that.
Exactly, that's right.
But your approach somehow gives a physical reason. Okay, for this reason, you are getting this, and
That's
there
exactly the point,
is no
right.
magic there, basically.
That's exactly the
Yeah.
point, because that's exactly because what would happen if the black holes would not get that entropy, then there would be mismatch between with cross sections, and that's impossible because gravity is a unitary theory, and string theory is a theory of gravity, and certainly it is unitary. At least the versions that we know, they're perfectly. So therefore, this explains why entropy could not have been anything else. That we were bound to get that entropy. Yeah.
Very nice. Okay, so I think Nirmal, do you still have a question, or is the hand from before?
I'm sorry.
Yeah.
Just one before.
Okay, don't worry. Okay. Okay, so if there are no other questions, then we thank Gia. Thank you very much, Gia. It was a very interesting talk.
Thank you very much for very interesting questions. Thank you.
Thank you.
A pleasure. Okay, bye.
Bye-bye.